Hello students, so in today's class we are going to learn a new topic under the first chapter, that is electric dipole in uniform and non-uniform electric field. So directly going into the topic, let us first see the first part, that is dipole in uniform field. Okay, that is basically dipole in a uniform electric field. So now here we need to know what is an uniform electric field and what is a non-uniform electric field. So basically uniform electric field is the one whose magnitude and direction remains same at all the points in a particular region. For example, this is the region I am considering. Okay, I am considering an electric field in this particular region over here. Okay, so if the magnitude and direction, since electric field is a vector quantity, if magnitude and direction of electric field at every point in this region is same, then we call that electric field as a uniform electric field. And what will be a non-uniform electric field? Supposing either magnitude or direction is different. Okay, one of the thing, that is magnitude or direction, has to be different, or both can be different. So at every point is supposing different, then that field is called as a non-uniform electric field. So this is a simple difference between a uniform electric field and a non-uniform electric field. So first what we are going to do is we are going to place a dipole in a uniform electric field and see what happens. So I'll give you just a brief idea, that is when you place an dipole, that is electric dipole, in a uniform electric field, a torque will be acting on that electric dipole and that electric dipole will start rotating. Okay, how we will see in the particular derivation. So let us directly go for the derivation under this topic, that is dipole in an uniform electric field. That is expression, we are going to derive here the expression for torque. And what is this torque? As I told you, when you place electric dipole in a uniform electric field, it will experience a torque, and we are going to find out the expression for this torque which is experienced by the electric dipole. So now let us consider an electric dipole which is consisting of, obviously electric dipole we know consists of opposite charges of equal magnitude, and there is a length of 2a, correct, between them, and let us consider it is placed in a uniform electric field E. So let me draw the figure over here. So let me draw the electric field first. Okay, so let us consider that this E is a uniform electric field. Okay, now let us place a electric dipole, that is a pair of equal and opposite charges separated by a particular distance, in this uniform electric field. So let me draw an electric dipole now. So yes, this is my electric dipole. Let's write down this as plus q here, plus q charge, this as a minus q charge over here. Okay, and they are separated by a distance of 2a. So let me mark the distance 2a in between them. So here this distance is 2a. You have to be very clear with your figures. Okay, this is your distance. Let us consider that this electric dipole is making an angle of theta with the electric field. Okay, the orientation of this dipole is such that it makes an angle of theta with the uniform electric field. So let me draw a line parallel to the electric field like this. Okay, and I say that the angle made by the dipole to the electric field, see, I'm drawing a line parallel, okay, to the electric field is theta. Okay, so for simplicity let me complete this triangle, because we are going to use this triangle in the further derivation. Okay, so now when we say electric dipole, we know one more term related to it, that is electric dipole moment, correct, which is q into 2a, that is either charge times the distance of separation between the charges, and it is a vector quantity and it very well has a direction, and the direction of this dipole moment is given from minus q to plus q. So let us mark that as well. So this is my electric dipole moment which points from minus q to plus q. Okay, so the magnitude of this dipole moment is given by, it will be P is equal to Q into 2A. This is the first step. Okay, first you have to write down the introduction part, which you will find in my notes, and then second part you have to write is magnitude of the dipole moment, which we already know, P is equal to Q into 2A. Okay, so now we know that when we place an electric charge in an electric field, what happens is that charge experiences a force. This is the basics, right? We have seen the expression, I'll write over here, we have seen the expression for electric field. E is equal to the Coulomb force upon the charge, the magnitude of the test charge which is experiencing the force. This is the expression we have seen, right? So from here we can write the force experienced by this test charge is equal to E times Q, correct? So now we also saw that, I'm just revising, for a positive charge, okay, F is Q times E. What does this mean? That F and E are in the same direction, correct? This is the thing we had seen, correct? And for a minus Q, what it means? F is minus Q times E. So what does this minus sign tells you? That F and E are opposite to each other. They are going opposite. If F is this way, E will be this way. That's what it tells. Okay. So simple logic over here. What these two statements tell you? That when you place an electric charge in an electric field, it will experience a force. This is the main point. Okay. The sections to it will be when you place a positive charge. Okay, what do you notice here? The force experienced by that positive charge is in the direction of electric field. So basically, this is my positive charge over here. So what will be the force experienced by this electric field? It is definitely going to be Q into E. And what is going to be the direction of that force? The direction of the force will be the same direction as the direction of E. The force and E will be in the same direction. That you have to note over here. Okay. Now there is a negative charge also here. Okay, so what is the magnitude of the force experienced by the negative charge? Minus Q into E. And what will be the direction? This negative signs tell us that F and E are in the opposite direction. So if E direction is this, the force experienced by this minus Q will be opposite. It is pointing this way, opposite to E. Okay, so now as we know, when a body experiences a force, supposing this is the pen, this body experiences a force, what happens is this body starts to move. Same thing is going to happen with these two charges. Once the forces are applied on these charges will tend to move. Okay, so let us first write down the expression for the force. Okay, so as we know, the force exerted on charge plus Q by the field E will be, it is going to be Q into E, and the direction of this force is going to be along E, since force and E are in the same direction. Again, the force experienced on exerted on charge minus Q by the electric field E will be minus Q into E, and the direction is going to be opposite to E. The direction is going to be opposite to E. So let us write down and mark the two forces in the figure. Okay, so if you see this figure here, the force on plus Q is going to be in the direction of E. The magnitude is Q into E, that is positive. Okay, and force on the negative charge is going to be opposite, so it's going to be minus Q into E, which is a vector. So these are going to be the two forces. Okay, so if we see these two forces, the magnitude is same, but the direction is different, right? But they are opposite. Okay, so what will be the net force acting on this dipole? So it is very much clear from here that the net force acting on this entire dipole, if you add it vectorially or if you add it with the magnitudes, it is definitely going to be 0, because if you see, Q is same, it's a dipole, right? So the charge magnitude is same. Electric field is uniform. So electric field over here and here is same again, correct? So this quantity and this quantity are same. One is positive, one is negative. So they will cancel out each other, and the net force acting on this dipole is definitely going to be 0. So let's write down that step now. So F total, okay, or F total or F net you can write, which will be equal to 1 is plus QE and 1 is minus QE. Okay, I'm just adding the two, and if you see here, this force, the net force or the total force acting on the dipole, turns out to be 0. Okay, so what can you say here is the net translating force on the dipole in a uniform electric field is 0. Okay, since there is no force acting, there won't be a translatory motion. Okay, this should be very much clear to you, a very important point. Okay, since the net force acting on the dipole is 0, there won't be any translatory motion. Correct? Translatory motion, you know, it's a sliding motion, for example. Okay, there would be a translatory motion. But if you see these two forces are not acting along a single line. What do I mean by that? Supposing I have a pen over here, I am applying a force this side and I am applying an equal force this side. Will this body move? No, this body will not move. Supposing I am applying 5 Newton this side and 5 Newton this side, equal and opposite forces. Okay, then definitely this body is not going to move from its position. This body will remain stationary. For example, I apply 10 Newtons over here, 5 Newton over here. Obviously this force is more, so body will move this side. Okay, or vice versa maybe. Okay, but since the forces are equal and opposite, the body is not going to move. But supposing I apply the force over here in this direction, down, I am pulling the pen down. Okay, and I am pulling the other end of the pen on top. Okay, supposing 5 Newton, equal forces. Now the body will move. Definitely the body is going to move. What is the difference? In the first case, when I was applying the force this way and this way, the force was collinear. Correct? The force was applied in a single line, in the same line. That is why the body was not moving and the force was equal, of course. Right? But in the second case, what is happening is the force is not collinear. Since the force application of the force, the point at which the forces are applied, are two different points. One is this way, one is this way. Correct? There are two different points which are away from each other and they are not collinear points. Right? The forces are, the points are collinear, but the forces are not collinear. They are not along the same line. One line is this way, another line is this way. Okay? So in that case, one more quantity comes into picture which we call as a torque. Correct? So this is the quantity which is torque, which comes into play over here. Since the forces are not collinear, we say that the torque will be applied on the body, and automatically, supposing I pull this down and push this up, this body is going to take a rotatory motion. That is why I said the statement is important here. The net force acting on the dipole is 0. That means there won't be any translatory motion. But if you see over here that the two forces are not collinear, so there will be some torque acting on this body. That body is basically a dipole, correct? So this torque will be responsible for the rotatory motion of the body or your electric dipole. Okay? So what we can say, the net translatory force on the dipole in a uniform electric field is 0, but two equal and opposite forces act at different points of the dipole, right? They form a couple. This is called as a couple, right? Okay, so this forms a couple which will definitely exert a torque. Okay, so let's find out the expression for this torque now. Okay, so from our basics, from our 11th standard, we very well know that the expression for torque is given as torque is equal to force. That may be either force, because the force which is applied is same, magnitude is same, right? So either force multiplied by perpendicular distance between the two forces, right? Now, what is going to be the force? Force is Q into E. I'm just considering the magnitude, no direction. So I'm just writing Q into E. No plus or minus, no vectors involved, okay? Multiplied by the perpendicular distance between the two forces. Now here, the distance between the two forces is not 2a, okay? We have written perpendicular distance over here. So what is perpendicular distance? It's going to be this distance, a direct distance between the two forces, that is this force and this force. So this distance we have to find out. Okay, so if you consider this right angle triangle, this is the right angle, this is my hypotenuse, correct, and this is my angle theta. So if I consider sine of theta over here, what do I write? Sine of theta is equal to opposite. So this is nothing but my perpendicular distance. So I'll write it as perpendicular distance. upon opposite side upon hypotenuse, that is 2a. So what is going to be my perpendicular distance from here? It's going to be 2a sine of theta. Correct? Let's substitute over here. The perpendicular distance we found as 2a sine of theta. Correct? So now can you tell me what is q into 2a? So if this is q here and there is 2a over here. So q into 2a is nothing but a electric dipole moment. So we can write very well torque. Torque symbol is tau, right? Basics again. So torque is equal to q into 2a is p. This e remains as it is, sine of theta. Correct? So PE sine of theta, can you express it in terms of vector? This is a formula for a cross product, right? So we can write this as P vector cross E. Correct? This is the formula for the cross product. PE A cross B is given by AB sine of theta, where theta is the angle between A and B, right? So using this basics, I can write this over here. So this is a cross product here. So obviously I have to have a vector on the other side. So torque is again a vector. Again, we know supposing A cross B is equal to vector C. What can we say about the direction of vector C? The direction of the vector C from our vector basics is, it is going to be perpendicular to the plane containing these two vectors, that is A and B. Correct? So direction of C is going to be perpendicular to the plane containing A and B. That is going to be the direction of the torque. So you can apply the right hand screw rule over here, okay, to get the direction of this torque. So supposing this is the plane containing P and E. Okay, so you can apply a screw rule, okay, right hand screw rule. You have to go from first vector to the second vector. Okay, you have studied this also in your 11th standard. Okay, and the direction of the thumb is going to give you the direction of the resultant vector, that it might be downward into the plane or out of the plane. Okay, depends how is your P and E. Okay, so that is going to be the direction of the torque. So basically this is going to be your final statement for the torque, that is torque is equal to PE sine theta, or torque vector is equal to P cross E. Okay, this is the statement you need to remember, okay, throughout your course, okay, or even after that. Fine. So now let us consider few notes. Okay, let's analyze this expression. So now in the analysis we have something called as stable equilibrium and unstable equilibrium. So what is stable equilibrium is if your P, that is dipole moment, is in the direction of E. That is basically, supposing, let's consider this is my figure, right? This is my dipole, let's consider. So basically this is my minus Q, this is my plus Q. Okay, this end, blue end is minus Q, silver end is plus Q. So dipole moment points in the direction of the pen. Okay, this arrow, let's say this is the arrow. Okay, so my P and E are in the same direction. The angle between them is 0. Okay, both are parallel. P and E are parallel. So that case is called as the stable equilibrium. So in this case, your P is parallel to E. So what will be theta in that case? Theta is going to be 0 degrees because both are parallel, right? And from the expression, if you see here, it is going to be PE sine of 0. Right? Theta is 0. So PE sine of 0 and sine of 0 is nothing but 0. So your torque will be equal to 0, or the magnitude of the torque in that case is equal to 0. So this is your stable equilibrium. Coming to the unstable equilibrium, supposing I keep my dipole reverse, like for example it was like this, correct, pointing in the direction of E. Now I just flip it on the other side. So my minus Q goes on this side, plus Q comes on this side. Okay, so dipole moment is pointing in this direction now. Okay, and E is originally in that direction, so both became reverse. Okay, so in that case what will be the theta? Theta in that case is going to be 180 degrees. Okay, so in this case P is anti-parallel to E. Okay, and in this case theta is going to be 180 degrees. And what is sine of 180 degrees? Here sine of 180 degrees is going to be 0, correct? And torque again is going to be 0. So in the stable equilibrium and unstable equilibrium, the net torque acting on an electric dipole is 0. That you need to understand over here. Okay. However, you can say that a dipole will be turning, okay, when it is kept in an unstable equilibrium. Okay, in that case there will be torque acting on it, okay, and it will be turning like this from unstable to stable. Okay, so that you need to remember here. So however, dipole will be turning by 180 degrees in 180 degrees by the torque. Okay, and this equilibrium is called as the unstable equilibrium. Okay, the third point here is what will happen if P is perpendicular to E. For example, P is like this, okay, or P is like this, okay, perpendicular to E. P is this way and E is this way. Okay, what will happen in that case? Okay, so if P is perpendicular to E, what will be theta in that case? Theta is going to be 90 degrees. Okay, and in that case your torque is going to be PE sine of 90, and sine of 90 is 1. Okay, so it's going to be P into E. So this is the maximum value of torque possible. Okay, so the torque will be maximum when your P is perpendicular to E. Okay, and the torque will be 0 when P is either parallel to E or P is anti-parallel to E. Okay, these are the 3 points. Okay, so basically what do we infer from here? So in a uniform electric field, dipole experiences only the torque, okay, and the net force acting on the dipole is 0. Hence what we can say? Hence the dipole experiences only rotational motion and no translational motion. Okay, this is very much clear from this derivation here, right? Okay, so now let us move on to the next topic, that is dipole in a non-uniform field. So as I told you, non-uniform field is basically a field wherein at every point the direction and the magnitude of the electric field is going to be different. Correct? So now what you need to understand over here is, in the previous case what was happening? Plus QE and minus QE were the two forces acting here. Okay, so there was plus QE and minus QE which was acting, but the magnitude, the direction was opposite, obviously, but the magnitude was same, right? Because Q and Q, the magnitude was same. E and E, magnitude was same because the field was uniform, right? It was a uniform field here. Okay, it was a uniform field, right? So basically the magnitude of the net force acting on each of the charges was equal. But now since we have placed this electric dipole in a non-uniform electric field, okay, Q and Q will have the same magnitude, no doubt, but E will be different. If this is E1, this will be E2 because it is a non-uniform electric field. At every point over here, the electric field is going to be different. Okay, so hence the forces acting are going to be different on each of the charge. So can we say that the net force acting on the dipole in a non-uniform electric field 0? No, we cannot say that. Okay, there will be some force acting on the dipole when it is placed in a non-uniform electric field. So I hope you understood the logic here. Q and Q will remain same, but E will be changing because it is a non-uniform electric field, and since E is changing, the force will change. Okay, by this formula here, force is E into Q. So Q will remain same, but E will change. So since E is changing, force will change. Okay, there will be a translatory motion in case of a when the electric dipole is placed in a non-uniform electric field. Okay, so coming back to the topic. Okay, so for a dipole in a non-uniform electric field, what we can say is, when a dipole is placed in a non-uniform electric field, dipole experiences both torque as well as force. The net force in this case is not going to be 0. Therefore, here dipole experiences both rotational as well as translatory motion. It is not just rotational motion. Okay, so now there are two cases over here when E and P are parallel to each other and E and P are in opposite direction. So we'll see each of this case in detail. Okay, so let's understand case 1 first. So case 1 is when E and P are in the same direction. So first let me draw an electric dipole. So let's say that this is minus Q and this is plus Q here. Okay, so this is the point, this is the line joining them. Let's mark our P. Okay, this is the direction of P, which is going from minus Q to plus Q. Okay, so let's consider, since the direction of P is this way, obviously the E direction has to be this way, because we have said that E and P are in the same direction. Okay, so this is our electric field direction over here. Okay, so now we know that when we place a positive charge in an electric field, the force on the positive charge is always in the direction of electric field. So obviously the force on this is going to be this way, in the direction of electric field. That is force on, I'll write over here, force on plus Q. And we know that when we place an negative charge on in an electric field, any electric field it may be, uniform or non-uniform, okay, the force experienced by it will be in the direction opposite to the electric field. So it is F is equal to minus Q into E, right? So it's going to be in the opposite direction. Okay, so E is this way, the force is this way, so this is going to be force on minus Q. Okay, so let us consider that E is increasing in this direction, okay, as the arrow is shown. So E is going on increasing, okay, the value of E is increasing this side. So obviously if it is increasing in this direction, electric field here will be higher as compared to the electric field over here. Okay, so if we need to find out the force acting on plus Q and minus Q separately, okay, which one will be greater? Obviously this one will be greater. So what is the formula for the force? Force is given by Q into E. Okay, so force on plus Q will be equal to plus Q into electric field at the position of plus Q here, correct? And force on minus Q is going to be minus Q into electric field at the location of minus Q. Now if you see, the charges are same, they are equal and opposite, correct? But only thing different over here is E plus Q and E minus Q. This is the term which is different. And which one is greater out of the two? E plus Q is greater, because I said that electric field is increasing in this direction, correct? So here electric field is higher at plus Q and electric field at minus Q is lower. So obviously the force on plus Q will be higher, that is F of plus Q is going to be higher than F of minus Q, that the force acting on the minus Q. So what is going to be the net, the direction of the net force? So basically the direction of net force is going to be obviously in the direction of the force on plus Q, because the force on plus Q we have seen is higher. So it's going to be this direction, this direction will be overpowering. Okay, and the direction of increasing field we already know. I'll just write it for a reference here, direction of increasing field. Okay, it's going to be again same. Okay, so what you see over here is the direction of the net force and direction of the increasing field is same. Okay, they are in the same direction. Now let us move on to the second case, that is case 2, when E and P are in the opposite direction. So let me draw a dipole again over here. So let's say that this is plus Q, this is minus Q. Okay, let me join the line between them. So our P is going to be now from minus Q to plus Q, so in this direction. Okay, P is going to be in this direction. Direction of E is going to be opposite to P, correct? So P is this way, so let me draw E the same way. Okay, this is my electric field direction. Okay, and again let's say in the direction of arrow the electric field is increasing. So as we go along P, that is the dipole moment, your electric field is decreasing. Okay, understand this. Okay, electric field is increasing this way, so along P electric field is decreasing, ulta, reverse. Fine. Okay, so now net force on a positive charge is always along the direction of field, so basically it's going to be in this direction. So this is the force on plus Q, okay, in the direction of electric field, and force on minus Q is always opposite in the direction of electric field, opposite to the direction of electric field. So now the field is increasing this way, so obviously the force on minus Q will be higher, correct, and the force on plus Q will be lower. Okay, so what will be the direction of the net force? It will be same as the direction of the force applied on the minus Q, because this will be higher, electric field is high over here. Okay, so direction of net force is going to be this direction, that is going to be this way. Okay, and direction of increasing field, as we have already noted down, it's going to be this way. So if you see, when E and P are opposite to each other, the direction of net force and the direction of increasing field is opposite. Okay, so this is all about your dipole, which is placed in a uniform field and non-uniform field. Okay, in the next class we are going to learn the expression for the potential energy which is stored in an electric dipole placed in a uniform electric field. Okay, so this is it for today. I'll see you in the next class.